Hello everyone, good morning from Tokyo. Welcome to my slide and very happy to have an opportunity of this presentation here. As introduced, I'm postdoc in NIPR and I have studied mineral dust on snow and ice in Asian and Arctic regions, focusing on their sources and transportation processes. Recently, I have tried to reconstruct variations in sources of mineral dust on the Greenland ice sheet from ice cores. Today, I'm going to talk about results from a northwestern Greenland ice core. Okay, let's start. So this picture shows the Kanak Glacier in northwestern Greenland. As you can see, the ice surface looks very green, but actually it contains various depositions transported from the atmosphere. For example, pollen, microbes, atmospheric dust, desert sand, volcanic dust, and sea salt. These deposits have been preserved in ice cores, and we can know the variation is seasonal, annual, and even in geologic timescale. So why Greenland ice core mineral dust is important? Past ice core dust records have significant variations in their concentration, composition, and morphology. And the variability is likely related to changes in atmospheric transport and environment of source areas. These are Greenland ice core records showing dust concentration and temperature change. There is a strong negative correlation between them. During the glacial period, dust concentration was substantially higher than interglacial, which attributed to change in aridity and dust storm activity in Central Asian desert, as well as atmospheric circulation patterns. In this way, ice core minerals can provide key information about global and local climate change. Sorry, I can't. Okay, so then where has Greenland ice core dust come from, and how can we identify their possible sources? One of the powerful tools is strontium, neodymium, and lead stable isotope analysis. These isotope ratios have strong regional variations and are less altered during transportation in the atmosphere or after deposition. And so they have been commonly used in ice core studies. This diagram is strontium neodymium isotopic ratios of mineral dust from Greenland ice cores and their possible sources. The ice core from inland ice sheet plotted here are close to Asian and African desert, while those from coastal ice sheet were close to Greenland moraine. According to the result, we can see there are mainly two possible sources for the Greenland ice core dust: distant desert and local sediment. The isotope analysis is very helpful for the source identification in this way. And actually, I also have used this for a long time. But unfortunately, there is a problem with this method. They need large numbers of samples for the analysis, and so have targeted mostly ice core dust from glacial periods characterized by a high dust concentration. So because of this, there is limited information on ice core dust source during interglacial periods. So we have developed a new method to identify ice core dust sources using SEM and EDS analysis. SEM image provides morphological information, and EDS provides a chemical composition of the individual particle. So from the EDS spectrum, we can identify minerals like this. These analyses allow the evaluation of the continental dust input and show variations in dust properties of low dust period of the ice core. So In this study, we analyzed minerals in a northwestern Greenland ice core over the past 100 years using this SEM EDS analysis. And we discussed the temporal variations in their sources. The ice core we analyzed was drilled in the coastal ice sheet of northwestern Greenland, called the Sigma D site in 2014. Total core length is 222 meters, and we estimate it's about 800 years old ice. And we analyzed the ice samples covering from 1915 to 2013. We used 4 square centimeters cross-section of the ice core. First, we scraped off the ice surface several millimeters with ceramic knife and corrected every 5-year intervals. Then freeze-dried the samples on a polycarbonate membrane filter and finally coated with vaporized platinum for SEM observation. We randomly chose 150 particles from a filter for each sample and measured the size with an image processing application. We also obtained measurement composition from the EDS spectra. Okay, let's move on to the result and the discussion. The left graph showed number size distribution of mineral dust in the Sigma D ice core from 1915 to 2013. And right graph shows its variation in average and maximum values. Most particles were less than 2 micrometers, which is consistent with the other Greenland ice core dust derived from distant desert. This means the ice core dust is also mainly long-range transported minerals. However, there are significant variations in mineral size among the samples. The samples from 1915 to 1950 and 1990 to 2013 contained larger amount of coarser particles than the other period. So this is likely to reflect variations in ice core dust sources. Then next, I want to look at the mineral composition result. The Sigma D ice core is mainly composed of silicate minerals, the most abundant family of crustal minerals. To identify their possible sources, we classified them into the following 5 types based on their formation processes and environments. So I would like to briefly explain about each type. First, type A is kaurinite, a clay mineral generally formed in warm and humid conditions and can indicate a contribution from low or mid-latitude areas. On the other hand, type B and C consist of mica, chlorite, and feldspats. They formed in cold and dry conditions and can indicate a contribution from high-latitude areas. Also, type D indicates a local, and type E indicates contribution from high latitude or desert. Okay, so let's take a look at the variation in the 5 types of minerals. This is a silicate mineral variations, and what we can see here is the composition significantly varied on multi-decadal scale. The proportion of type A, most dominant minerals in the ice core indicated by orange, was high from 1950 to 2000, but low in the other period. In contrast, type B, C, D, and E minerals showed the opposite trend. From these results, we can see the ice core dust originated from mainly 2 different geological sources in different periods during the past 100 years. So what is the possible causes of the compositional variations? These are variations in each mineral type proportion, and the bottom shows surface temperature anomaly change in northwestern and entire Greenland. We know that there were 2 warm and one cold period over the past 100 years in Greenland. The mineral variations are well consistent with the temperature change. The proportion of type A, this orange, was high during the cold, but low during the warm period. In contrast, as I already mentioned in the last slide, the proportion of type B to E showed opposite trend. Therefore, the multi-decadal variations in the silicate minerals were likely affected by local temperature changes in Greenland. Based on the dominant mineral types, high latitude, desert, local areas are likely candidates for dust sources in warm periods and low to mid-latitude areas in cold periods. Then finally, let's find an answer to the question, where has the ice core dust come from? We calculated the probability distribution of an air mass arriving at the sigma D site from these four land regions with these trajectory settings. The left graph shows seasonal, and right graph shows annual variation in the regional contribution through wet and dry deposition. As shown in the figures, most of the air mass came from the western coast of Greenland, and a smaller proportion came from northern Canada. The contribution from the two regions has not significantly changed over the last 5 decades, so the variation in the ice core dust sources were unlikely due to changes in air mass transportation. And so what affects dust source variability? Our result indicates it could be a change in the surface condition of the source regions. The top graph shows surface temperature variations in Greenland again, and the bottom shows variation in snow cover fraction anomaly on the western coast of Greenland during summer. There is a negative correlation between them, implying the snow cover duration was shortened in the warming periods. Furthermore, recent warming has accelerated retreat of the ice sheet and local glacier in Greenland since 2000, increasing the exposure of the ground surface in snow ice-covered areas in coastal region like this. In short, the retreating ice and decreasing seasonal snow likely contributed to the increase in local dust emissions to the sigma D site in warming periods. On the contrary, ice core dust might come from low or mid-latitude in the cold period because the dominant mineral types, this orange, are generally formed in warm and humid areas. However, our trajectory analysis suggests little contribution from these regions. So where is the possible source? According to previous studies, marine sediment from northern Canada contained abundant type A, this orange, likely formed in the past warming event in non-marine environments. Contribution from northern Canada is the second most in our trajectory, and so we concluded such ancient deposit in northern Canada is likely the best candidate for the ice core dust source during the cold period. Okay, so let me summarize our result. We analyzed mineral dust from the sigma D ice core dust and demonstrated the first high temporal resolution record of mineral composition in a Greenland ice core over the past 100 years. The proportion of type A mineral is relatively higher in almost all the period, so the ice core dust was constantly supplied from northern Canada to the sigma D. However, dust was additionally provided from local ice-free areas in the warm periods because of shorter snow ice cover duration in the coastal region during melt season. We also suggest the SEMEDS analysis can detect variations in ice core dust sources during recent period of low dust concentrations. For the next step, I'd like to reveal spatial variations in mineral dust source among Greenland. So I have analyzed dust in the East Grip ice core obtained from more inland ice sheet using SEM and EDS and compared it with the sigma D. I hope to have an exciting result. Thank you very much.
Thank you very much indeed. So as I said initially, we usually keep the questions to the end. So if people want to keep a note of those, or you can put them on the chat now and we'll ask them at the end.
Okay.
The second speaker in this series of speakers from Japan is Ikumi Oyabu, also from the National Institute of Polar Research in Tokyo. So I see you've shared your slides. Are you able to show yourself on the video?
Can you hear me?
We can hear you. Yeah, that's fantastic. For a moment, we had no image of you, but that's perfect.
Okay, thank you very much. So good evening, hello, and good morning, everyone. I'm Ikumi Oyabu of National Institute of Polar Research. So thank you very much for providing me such a nice opportunity to introduce our study. I'm working on air compositions in ice cores, such as greenhouse gases or isotopic compositions of oxygen, nitrogen, or argon usually. But today I'm going to show you about surface mass balance around Dome Fuji on behalf of co-authors and all contributors of Japanese Antarctic research expedition. I think this topic may be more suitable for this seminar. Recently, I compiled all the new shallow ice core data collected by Japanese Antarctic research expedition and reconstructed SMB history for the last 5 kilo years. This work has just been accepted last week in Climate of the Past. Recent studies with remote sensing observation combined with modeling of regional climate and glacial isostatic adjustment have shown that Antarctic ice sheet has been losing its mass over the past 2 decades. The ice mass loss is enhanced in Antarctic Peninsula and West Antarctica, mainly due to basal melting of ice shelves and acceleration of glacial flow. On the other hand, the ice mass in Dronning Maud Land is significantly increased over the past decade, possibly because of the increase in snow accumulation. So remote sensing observations are useful, but they are available only over the last few decades. The Antarctic ice sheet also changes in much longer time scales than those covered by the direct observations, so the long-term record of the SMB are needed to better understand the Antarctic ice sheet mass changes. Fern and ice cores have provided the accumulation histories for much longer time scales. There are mainly 2 methods to reconstruct. One is that mean accumulation rate between dated horizons are calculated by dividing the depth difference between age markers corrected for firm density and layer thinning. This method requires precise age scale. The longest reconstruction from the inland East Antarctica with this method is about 2 kilo years. Another method is scaling of the stable water isotope ratios, which is more common method for ice core study. This study, I used first method. Let me introduce previous studies. Thomas et al. 2017 compiled 79 records from ice cores over the past 1,000 years. The analysis of the total Antarctic SMB derived from the database suggested that snow accumulation had significantly increased in the 20th century. But if I focus on the East Antarctic Plateau, individual studies do not show a uniform trend over the last century. Some sites showed an increase in accumulation rate, while others showed a decrease. Such inconsistent trend of the surface mass balance over the East Antarctic Plateau may be related to their locations relative to the ice ridges and predominant wind directions, or the influences of atmospheric circulation patterns. For the longer time period, only 4 ice core records actually extend to more than 1,000 years, which are marked by red, and the vast interior of the East Antarctic ice sheet is not represented. The authors suggested that small changes in the accumulation rate in the East Antarctic Plateau could change the sign and significance of the total Antarctic surface mass balance trend, because the total area of the East Antarctic Plateau account very large areas. So reliable long-term surface mass balance records from East Antarctic Plateau are necessary. However, there are some issues and difficulties for surface mass balance reconstructions from East Antarctic Plateau. For example, difficult to access to the observation site, and the top part of the shallow course are extremely fragile. Snow deposition is not spatially and temporally uniform, so annual layers can be eroded. Density profiles are highly variable, and sparseness of volcanic eruption records before 1,000 common era, so it makes it difficult to precisely date ice cores. So we are not sure how much one ice core record from East Antarctic Plateau represents around the study region, but if we could collect many cores, we may obtain much more robust information around the region. So in this study, we reconstructed surface mass balance histories around the Dome Fuji over the last 5 years from 13 ice cores and 7 snow pits collected by Japanese Antarctic Research Expedition over the last 30 years. The study area is inland Dronning Maud Land around Dome Fuji station. As I said, we used 13 of ice cores and 7 snow pit samples. Generally, air mass with moisture comes from this direction to inland sites, so the surface mass balance is larger on the windward side of the ice divide than on the leeward side. Here is the data set I used in this study. I don't explain this data in detail, but thanks to so much numerous data, we could reconstruct precise accumulation histories. I really appreciate all contributors. For ice core dating, each ice core was synchronized to the west divide core instead of using the year of volcanic eruption. The chronology of the west divide core is one of the most precise chronology in Antarctica. The volcanic eruption record before 1,000 common era is surpassed, as I said, so it has been difficult to precisely date ice cores from low accumulation area. But thanks to the west divide core, we became able to date such ice cores more precisely than before. Thinning function is also important, but we know only the thinning profile of Dome Fuji, so we scaled Dome Fuji thinning function by ice thickness at each drilling site. Here it is the result of the accumulation reconstructions from 13 drilling sites. MD364 is on the way to Dome Fuji station and located at north of Dome Fuji. DFNW is located at northwest of Dome Fuji. DF1, DF1997, and DF2 are from Dome Fuji station, and DFS are located at about 10 kilometers south of Dome Fuji. DFSE is located at southeast of Dome Fuji. And NDFN and NDF sites are located at about 50 kilometers south of Dome Fuji. And S79 and S80 are located further south of Dome Fuji station. So from these records, we find clear decreasing trend from 6 cores covering more than 2,000 years, which are DF1, DF2, DFS, NDFN, and NDF 2018. We also found increasing trend for the last 200 years at most of the sites. Let's look at the spatial distribution for the first. This figure shows mean accumulation rate for the 3 time period. Focusing on around Dome Fuji station, this region, accumulation rate at GIF NW, which is here. This is larger than Dome Fuji. GIF NW is located at the windward of the ice divide. NDF, which is here, this is smaller than Dome Fuji. The site is located at the leeward of the ice divide. And DFS is located up about 10 kilometers south of Dome Fuji, and the accumulation rate is slightly smaller than Dome Fuji, but larger than NDF. This spatial distribution is also confirmed in longer time period, this figure and this figure. Such clear spatial gradient around Dome Fuji depends on the site location relative to the ice ridges combined with predominant wind directions and proximity to the ocean. To robustly estimate the trend and variability of accumulation rate in the Dome Fuji area, we constructed accumulation rate from the individual cores. This stack includes 10 ice core data around Dome Fuji. We found two important features in the stack. One is that the magnitude of the increase in accumulation rate during the last 150 years is the greatest in the last 5 kiloyears. This may be due to the combination of the anthropogenic greenhouse gas increase and stratospheric ozone depletion, as previous studies suggested, and the very low accumulation in the 18th to 19th century. Second is there is a significant long-term decreasing trend over the last 5 kiloyears. To my knowledge, this is confirmed for the first time in East Antarctic Plateau. We explored possible cause for the long-term decreasing trend. The first obvious candidate for the long-term change is the decrease in annual mean insolation at high latitude. This may cool the ocean surface and atmosphere over the Southern Ocean and Antarctica, which lead to reduced evaporation and atmospheric moisture content and decrease in the snow accumulation over the Antarctic inland. A recent study with climate models suggested that surface mass balance variations are related to the surface temperature and sea ice extent. So we compare our SMB trend with published temperature and sea ice reconstructions over the latter half of the Holocene next. Temperature reconstructions showed long-term cooling in Southern Hemisphere. And water stop ratios from East Antarctic ice cores commonly showed decreasing trend from the mid to late Holocene. And from a study on marine sediment cores, Dennis et al. 2010 suggested that increasing of sea ice cover over the late Holocene is common feature in coastal Antarctic area. And finally, Antarctic ice cores show secular increases in sea salt sodium, which is a proxy for sea ice extent in Southern Ocean. So the long-term trend may possibly be due to long-term surface cooling over the Southern Ocean and East Antarctica and sea ice expansion in moisture source area. Next, I will show you centennial scale variations. From the Dome Fuji stack, there is some variation like large, small, and rapidly increase. This variation is consistent with previous surface mass balance reconstructions in East Antarctica for the last 700 years. This is stack from Dronning Maud Land and East Antarctic Plateau, East Antarctica. They showed that like large, small, and increase. So previous studies have suggested that period of small surface mass balance are related to the solar minima, like a stellar or Maunder minima, or strong volcanic forcing over the last millennium, possibly through the reduction of incoming solar radiation and associated changes in climate system, such as surface cooling and atmospheric circulation changes. However, the correspondence between the SMB anomalies and climatic forcing is not clear older than 700 years ago and further back in time. So this figure shows the Dome Fuji surface mass balance trend, variability, and climate forcing for the last 5 kiloyears. The surface mass balance anomaly does not always correspond to weak solar minima or strong volcanic activity. Before 1000 common era, this time period, the average solar activity was larger and frequency of large volcanic eruption was lower than during the last 1000 years. It might be possible that a clear relationship between the significant negative surface mass balance anomalies and solar and volcanic forcing is only visible when the two forcing anomalies are strong and coincide. There is also a possibility that surface mass balance variability is not well captured by our stack because of the fewer number of ice cores for the period and age constraints. In any case, it is desirable to obtain long-term and detailed reconstructions of Antarctic ice sheet surface mass balance at multiple sites to examine their relationships with the climate forcing. Okay, this is my last slide. So we showed 13 accumulation histories around Dome Fuji over the last 5 kiloyears. So the most important finding in our result is a long-term decreasing trend for the last 5 kiloyears. We speculate that this long-term trend is maybe due to long-term surface cooling over the Southern Ocean and East Antarctica and sea ice expansion in moisture source area. And also the magnitude of the increase in accumulation rate during the last 150 years is the greatest in the last 5 kiloyears. And also we found some centennial scale variations. For the last 700 years, the variations are generally consistent with previous reconstructions, but all the time period, we don't find correspondence between volcanic forcing or solar activity as previous studies suggested. Okay, that's it. Thank you very much for attention.
Thank you very much indeed. So the third speaker of our three is going to remain in Antarctica, and it's Kino Kanon from the University of Tokyo.
Yes, so can you see my screen now?
Yes, we can see your screen, yes.
Okay, then let's start. Yes, so my presentation title is Influence of the Southern Westerly Winds on Precipitation Water Isotopes Inland Antarctica. So my name is Kanon Kino from the University of Tokyo, and I really appreciate inviting me to this wonderful seminar. And myself, I'm a climate modeler and interested in the paleoclimate. But in today's presentation, I mostly talk about our paper published in 2021. It's for the modern climate. This is because during my PhD, I realized that if we want to know the past climates, we have to understand the modern climate first. Yes. And I also briefly mention another work for the last glacial maximum, which is going to be submitted to JRL soon. So, yeah, water isotope ratios, such as the O18, recorded in Antarctic ice cores, is the typical temperature process for the past climate, paleoclimate. In traditional ice core studies, they assume calm climate in inland Antarctica, like here. So they're the persistent inversion layer in inland Antarctica. And there's a constant relationship between mean condensation and surface air temperatures. So with this assumption, the empirical isotope thermometers can linearly convert the isotope ratio to temperatures. And the one-dimensional model can simulate the transportation of the water isotopes from low latitude to Antarctica. However, the Antarctic weather is dynamic, not always calm, even in inland. So in this figure, black line is the Antarctic ice sheet. Sorry for very rough drawing here. And the blue line is the sea ice, and the orange lines are the clouds. So here I'd like to start animation here. So here you can see that the clouds flow from the west to east, and it sometimes intrude into Antarctica. So these dynamical changes, this kind of changes are associated with high pressure, low pressure systems. And such warm and humid air intrusion into Antarctica can induce extreme large precipitation as events. So recent studies have suggested such dynamical system is potentially important to understand ice core records, including isotope signals. So the point is we need to revise our understanding of how Antarctic weighting determined and this is because our understanding of Antarctic weather has been updated. So to tackle this problem, several previous studies analyzed a few typical events or classified daily weather patterns in the modern climate, but they haven't been confirmed statistically. This is because of the limitation of the observed daily precipitation isotopes in inland Antarctica. So for paleoclimate studies, estimating the potential impact of such extreme precipitation events, it's still a big issue. So in this study, I used an isotope-enabled version of climate model. It's named NIRC5 ISO. So by using this one, statistical association between the atmospheric circulation and precipitation water isotope variation at Dome Fuji was investigated. Yeah, this study focused on Dome Fuji, that is the Japanese Antarctic station, one of the inland Antarctic ice core sites. And we did experiments for the 30 years from 1981 to 2010. And the model was nudged, the horizontal winds toward the reanalysis data set. And the spatial resolution of this model was set to about 200 kilometers. So you may feel that it is too coarse, but it is still enough to simulate high pressure, low pressure systems. Then results. Firstly, I evaluated the model with a 1-year observation at Dome Fuji, black as the observation and red as the modeling results. From the top, the weighting precipitation, surface area temperature, and precipitation. So each variable, for every variable, our model successfully reproduced the observed patterns, observed daily patterns very well. So for example, in here, when the temperature increases, the weighting precipitation also increases, and it accompanied relatively large amount of precipitation. And another point here is our model reproduced the seasonality of amplitude of daily signals. So it means that during the austral winter, the amplitude of daily signal is about 10 degree or 10 per mil in isotope and temperatures. On the other hand, during the austral summer, they are less amplified. And from here, I show the results for the whole 30 years climatological analysis. They are the monthly means, red as temperature and blue as the weighting precipitation and yellow as precipitation. And here, dashed lines are the weighting mean by the daily precipitation amount, and the solid lines are the arithmetic mean without precipitation weighting. So using ice cores, we assume we can reconstruct temperature as in the solid left line, this one. But however, ice cores should record the dashed lines because it should be always weighted by precipitation amount. So from here, this result suggests that the warm bias should exist in the austral winter, and it's about 11 degrees in case of this experiment. On the other hand, in austral summer, the differences between solid and dashed lines are less different. So it means less bias. This is because the small variability or amplitude in daily signals, as shown in the previous slide here. Yes, and so this results also suggest that the Austral winters, to understand the determination process during the Austral winter is more important and essential. So from here, I'm now focusing on the atmospheric circulation. So here, using 30-year time series of isotope signals in precipitation as Dome Fuji as an index, I classified each day as heavier isotope days or lighter isotope days, then made composites of difference of geopotential height by heavy isotope days minus light isotope days. From here, this study found that this typical pattern for isotope signal at Dome Fuji is very similar to the right figure, negative pattern of the southern annual mode, SUM. And the middle figure is same as the left one, but only for the Austral winter. And this is more similar to the negative SUM pattern in the right. So what is the SUM? SUM is the southern annular mode. It's the first atmospheric circulation mode in the southern mid-high latitude. And it is an indicator for the southern westerly winds. Our further analysis showed that when the SUM is in the negative phase, southern westerly winds become weak, and number of blotting events increased around Dome Fuji. And the blotting events enabled warm and humid air intrusion to Dome Fuji and resulted in high day weighting precipitation there. I explain how the SUM modified the relationship between isotopes and temperature at Dome Fuji. This is the bubble chart with histograms. The x-axis is temperature and y-axis is day weighting precipitation. And the size of each bubble shows the precipitation amount of each day. And the red color is some negative and blue color is some positive. And the bold lines are the linear regression lines. So from this figure, we can see a systematical shift induced by SUM. Yeah, so the day weighting precipitation in some negative is higher, about 10 per mil compared to the SUM positive. So it means that even for the same temperature at Dome Fuji, the precipitation isotope should be different between some positive and some negative. And for precipitation amount, precipitation mainly occurs under some negative conditions, so it suggests that accumulated snow would bias towards some negative. We conducted composite analysis again. There are composites between some minus and some positive for the Austral winter, surface air temperature, precipitation, and day weighting precipitation. So every variable increased in almost all regions of Antarctica. And the increases were largest around Dome Fuji. But on the other hand, it was less sensitive around Dome Sea, which is also an ice core site in inland Eastern Antarctica. So it means that Dome Fuji is located in the most sensitive regions to SUM, but not for Dome Sea. These locational features warn us to consider these sites together when we interpret the ice core records. We have to carefully think about the differences among sites. Yes, until now I talk about the study for the modern climate, but from now I'd like to briefly talk about another study for the past climate. So the target period is the last glacial maximum, LGM. LGM in 21,000 years ago was the extremely cold era characterized by very low atmospheric CO2 level and a huge ice sheet in the northern hemisphere. In a modern climate, the ice sheet only existed in Greenland and Antarctica, but in LGM, North America and Europe are also covered by the ice sheet. So by using the same isotope-enabled climate atmospheric model, I simulated some probable LGM climates. It means that the detail of LGM climate is still argued. So I input 2 different sea surface reconstruction into the climate model and reproduce the probable LGM climate. In these figures, colors show the annual mean SST, sea surface temperature as LGM minus PI, and contours show the sea ice area in each climate. The left one is the statistical reconstruction using multi-processes, and the right one is the output from a climate model. And this study conducted 4 experiments: pre-industrial, LGM-G with this one, LGM-M with this one, and the long name one. And so in LGM-M with G ice, SST was set to be same as LGM-M, but the sea ice around Antarctica was set to be same as LGM-G. This kind of experiments are called sensitivity experiments. It is the very general and typical way in climate modeling studies to decompose the role of SST and sea ice. So because of time limitation, I briefly explain our main result about the climatological impact of the SST. So here I show the schematic view. When the SST meridional gradient increased, it means that warm in low latitude and cold in high latitudes, westerly winds in about the Southern Ocean were intensified. This is because increasing of atmospheric baroclinicity and storm track activities. And it also increased the southward warm and humid airflow. And this steeper SST gradient also increased the evaporation in low latitude and decreased evaporation in high latitudes. So this top right figure shows the annual zonal mean of the atmosphere in the model coordination. So here is the surface. So the reddish color, the red color indicates the atmospheric warming in low latitudes, but over Antarctica, we cannot see surface temperature changes. But still, the air intrusion from low latitudes to Antarctica is shown by the green dashed contours. That contains lots of heavy waters, resulted in the increases in the weight in precipitation over Antarctica. So, and the feature of the westerly winds in LGM, it's not revealed, it's still under discussion, but our results suggested that if the westerly in LGM were strong compared to the present climate, it will increase the Antarctic their weighting. And it also changed the relationship between the temperature on Antarctica. Yes, here's the conclusion and summary. So we found a strong association between the southern westerly winds and their weight in precipitation in inland East Antarctica. And warm and humid air intrusion from the ocean is the key process here. Yeah. And the biggest remaining issue now I have is that we haven't investigated the relationship between DXS, the secondary isotopes indicators, and the southern westerly winds. Yeah, this is the next work for me. That's all. Thank you.
Thank you very much indeed. So we'll open it up to questions for all 3 speakers. So if anyone has a question, if they would like to just indicate on the chat, and then you can unmute yourself and ask your question. These were absolutely wonderful talks by everyone, and so strongly linked as well. That's a real theme within the presentations. So, Yuko, would you like to unmute yourself?
Can you hear me?
Yeah, perfect.
I'm Yuko Mochizuki of Riken, Japan. And first of all, I would like to say it's very nice to see 3 young Japanese researchers at this meeting. because this is a kind of rare, I think, in the very traditional cultures of Japan. Anyway, congratulations for all three. And I'd like to have questions for each. Now, for the first question for the Nagatsuka-san. Okay. Sorry if I missed your point, but sorry if I missed your point, but you showed the change of climate in the past, about 1,000, 100 years.
Yeah, 100 years, yeah, I showed.
Yes, and you saw the change of the climate like this.
You mean the mineral composition?
Yes, yes.
Yes, yeah.
Yes. And have you considered the relationship between the change of the climate with the change of solar activity, as Ikumi-san, Oyabu-san have just showed that? Because the middle region of your research is, I think, maybe correspond to the high solar activity period called modern maximum. So I don't know negative relationship or positive relationship, but maybe it's worth to check the relationship even for the Greenland ice cores, I think.
Yeah, thank you for your comments. Unfortunately, this time I only compared the mineral composition with a temperature change. So this time, and furthermore, I focused on the mineral size, and in the warmer period, the coarser particles increased. So I think the local things increasing in warmer period related to temperature change, because melting of the ice can exposure the surface soils around the glacier, and it can be new source for the warming period. So I would say the temperature is the most possible cause for the mineral composition in the sigma D ice core. But I have to also check the things suggested by you and the solar activity. Yeah, I'd like to check it.
Yes, please.
Yeah, thank you very much.
And for Ikumi-san, may I ask a question? Your results are very nice to show the obliqueness and the local insulation, the tendency for longer period. And my question is that if you consider much more shorter variations of obliqueness, insulation, then is it possible to find multi-decadal relationship in your results for the accumulation rate or surface mass balance?
Okay, thank you very much for your question. Unfortunately, the Dome Fuji region is very low accumulation, so it is difficult to date, difficult for annual layer counting. So I think it is difficult to see multi-decadal variations because volcanic signals is located only about few decades or sometimes every 100 years or several hundred years. So I think it is very difficult to reconstruct shorter variation, shorter than decadal variation. So I think it is difficult to see the relationship between shorter time period of solar activity and surface mass balance around Dome Fuji.
I think I agree with you in the sense of it's difficult for the to extract annual variations from Dome Fuji stations, but we have, our group has found that there is decadal and multi-decadal relationship in nitrate variations in a Dome Fuji ice core. So it may be possible, even for South mass balance, to find 10 or 100-year scale variations if you consider some kind of the method to include the variation from the insulations, I thought. Yes, thank you very much. I'm sorry. And I'm sorry taking a time for me, but this is my last question to Kino-san. And you said that Dome Fuji, I am very interested in the difference between Dome Fuji station, Dome Fuji ice core and other Antarctic ice core like Dome C from ice cores from Dome C. And Kino-san mentioned that the Dome Fuji ice core is very sensitive to some modes, right? But not ice cores from Dome C. My question is why?
Yeah, thank you for asking. Yeah, it's basically because of the teleconnection pattern around on Antarctica. So in case of the West Antarctica or Dome C, so it's also have some connection with ENSO, for example. Like including the PSA pattern, like PSA patterns. So my understanding is more complicated Dome Fuji. In case of Dome Fuji, there are no, of course, the some also associated with ENSO, but basically, the Dome Fuji area is the east part of East Plateau. It's more, simpler than other regions. That is my understanding.
Simpler, what means simpler? You mean?
So it means that if we do the same analysis for the Dome C or other regions, we should take into account both SAM and PSA patterns. Yeah, it's very complicated combination of the several teleconnection patterns. But in case of Dome Fuji, it seems that the sun is dominates that region.
I see. Thank you very much. That's
Thank
all.
you for asking.
Thank you very much for your questions. Roger, I think you have a question.
Yes, thanks to all three speakers, and apologies, I just have one question for our first speaker.
Me? Yeah.
Yep, thank you. Yeah, hello.
Yes, thank you. Hello.
I had already written down what sort of spatial variation do you find, and then I saw your last slide that what you want to do.
My last slide. Okay.
Yeah, what you want to do is to look at the variation in other places in Greenland.
Yes, okay, I share my slide. This slide?
Okay, a little bit earlier than that. You showed a picture with 2 other sites in Greenland that you want to study in future.
Okay, I see.
Yeah, and I had already written down what sort of spatial variation.
This one?
Yeah, that's it. Thank you.
Yeah.
So I guess my question is, what sort of spatial variation do you expect?
Okay.
When you get to
Actually,
study them, given the kind of wind patterns that exist over Greenland?
Actually, thank you very much for your question. And actually, I have almost completed to analyze the East Grip ice core. And for now, I can see significant difference between East Grip and Sigma. And the most difference point is the mineral dust in the East Grip ice core is likely derived from more distant than sigma. I mean the local dust, there is smaller amount local dust in the east strip than sigma.
Mhm.
Yeah, because it's actually we can easily guess because eclipse is located more inland than the sigma, and furthermore the other different point is sigma is mainly sigma dust is mainly came from northern Canada, but east strip is not. Maybe from more Eurasia or some part from Asia. So I think this difference was caused by the different pattern of atmospheric transportation. So sigma atmosphere, the air mass of sigma came from western, but that of east strip
Yes.
probably from the south or east.
If I remember correctly, you go back to 1950 with your data.
Yeah.
So you will have potentially data on radionuclides from atmospheric nuclear tests. That would be an interesting thing to look at as well.
Yeah. 1950. Yeah. I also back to 1910, so we can compare the same 100 years between them.
Cool.
So yeah, I would like to focus on this year.
Smashing. Thanks very much. Good luck. Good luck with
Yeah,
your
thank you
studies.
very much. Yeah, thank you.
Thank you very much indeed. Are there any further questions for any of our speakers from the audience? Roland.
Thank you, Tavi. I just don't type fast enough.
That's fine.
Me?
That's much nicer
My
to
que-
hear people talk anyway and see their
No.
faces.
So you might even be able to see me now. So my question was for our first speaker. So thank you for your very nice presentation.
Yeah, thank you.
Focused on the relative proportions of the dust types in your analysis.
Yeah.
Is it informative to look at the time variations of fluxes of individual classes? For example, whether that distance supply was relatively constant and the change in proportions was due to the variations of the local Greenland source that you discussed in some detail.
Distance. So you mean the, sorry, can I share my slide?
Yes, what I mean is that when you look at relative abundance, this is obviously a zero-sum game.
Yeah.
More of one thing means less of another.
Yeah.
Now,
You mean the proportion?
Yeah. So you described
Okay.
the variation here as explicable by variations in those local Greenland sources, which were temperature controlled.
Yeah, temperature, yeah.
Presumably you can individually consider the flux of the different classes to decide, for instance, was the distant source still providing dust at the same rate? It just made a small proportion changed as well.
So maybe I also analyze the dust with the different sides, and so the result shows the coarser. I show the 3 different sides of the dust, and yeah, these all show the higher concentration than the higher concentration in warm periods than the cold periods. So I guess one most possible reason is temperature, but I would say also the other reason can affect the different pattern of the composition. And for example, how to say, sorry, could you say again the question, your question?
Okay, I mean, it's obviously, I mean, I guess analytically, it's much easier to find the proportions of the different classes. It would be interesting if you were able to give an absolute measure of the flux of particles of a particular class.
Okay.
You see, if you take size, then presumably you get fine as well as coarse grains from a local source.
Okay. Actually, I analyzed the particle size of each mineral type, but I can't show in this presentation. But the coarser particles, I mean, in this presentation, type B, C, D, E are likely derived from local, and they have coarser particles than the type A.
Yeah, I can't quite read the scale there. Is that the absolute count of part A or of type A, or is that the proportion?
Not proportion, but I count 150 particles of each. So I only show the proportion in this presentation, but mostly this is similar to the individual number of the particles to the proportion. So there is not so difference between proportion and number of the particles of each type.
I think.
Okay, thank you.
Can I answer your question? Sorry.
Was that the answer you were looking for, Roland, or were you wondering whether one part of the ice core was completely black and another part was completely white, but the proportion might be the same?
Yeah.
Well, what I was concerned about is that if you have more of everything, less of everything, then obviously the proportions stay the same. If you have a constant supply of one class and a varying supply of one of the others, then the proportions change. But you would learn about you mentioned the ability to probe more global aspects of climate. If the supply of dust for instance, if the supply of dust from the Canadian source was relatively constant, then that would tell you something about the long range weather systems. If it was also changing, but just an effect that you didn't see because of the big variations in the local Greenland sources, then the issue would be more complicated. That's all.
Yeah, thank you.
Thanks.
Yeah, thank you very much.
Thank you very much. There's a comment from Kanon in the chat. I don't know if you want to follow that up or whether there are any further questions for anyone. We're kind of losing people, I guess, we're after the hour, so some people have classes and so on. Okay, well, a huge thank you to everyone, especially those people who got up so early to give the seminars and to be audience. And just again, to say a huge appreciation for how international this audience has been. I think we had most of the continents on the planet represented in the audience. So thank you very much indeed for 3 fantastic talks, and thank you very much for the audience for coming along at all different times of the day. So see you at the next seminar, which is next week. Thanks very much.